Hi, this is Zack Slepian, and today I'm here to tell you about parity violation in the galaxy 4-point correlation function. This is work done in collaboration with Alex Królewski at Waterloo, Simon May at Waterloo, and my team at UF, including Alessandro Greco, William Ortola-Leonard, and Farshad Kamala-Nehad. So, how can we search for parity violation in the early universe? Well, with this background image, I'm giving you a hint. These are the 777,202 luminous red galaxies of Baryon Oscillation Spectroscopic Survey CMAS sample, which was, until DESI, the largest suitable sample for a parity violation search. The color coding is telling us the redshift. The redder galaxies are farther away. The more yellow ones closer to us. And so with these redshifts, we know the 3D positions of the galaxies. Certainly we can clearly observe the left, right, and up, down, or RA and DEC positions, and the redshift gives us the distance along the line of sight. So in this talk, I'm going to talk to you about how we can use 3D galaxy positions to search for parity violation. So for parity, we need a 3D statistic. The 2-point correlation function describes a line, 2 points separated by a line. And you can imagine looking at the 2-point function in the mirror, which is what parity essentially is, and the 2-point would look the same. A line is a line in the mirror. The 3-point correlation function describes correlations of triplets of points. The geometry is a triangle. Now, a triangle defines a plane, and a triangle's mirror image can be rotated into itself in 3D. So under rotations, triangles are also not enough to distinguish parity. However, the 4-point function is sufficient to distinguish parity, as you can easily see by putting one galaxy at the knuckle of your middle finger on your right hand, and 3 galaxies at your middle finger and 2 other fingers' fingertips on your right hand, and then doing the same with your left hand. What you'll see is that you can't take the tetrahedron formed on your right hand and rotate it into the one formed on your left hand. You've produced 2 distinct mirror image tetrahedrons that cannot be made into each other by rotation. So the galaxy 4-point correlation function is a tool we can use for parity. Formally, it's the lowest order 3D statistic, and it represents the excess of tetrahedra over what a spatially random distribution would have. And as you can tell by rotating your right hand and left hand around and moving them left, right, and up, down, it's rotation and translation invariant, and this corresponds to the cosmological assumptions of isotropy and homogeneity. So we need now to know what's the right mathematical way to describe the 4-point function, or tetrahedra. So it turns out that it's not such a trivial question, and the answer is to use a set of basis functions that we call the isotropic basis because they're rotation invariant. What we do, starting at the equation at upper left, is we take the 4-point correlation function and we decompose it into this basis, which are these script p functions underlined in gold. And once we've decomposed it in this basis, all the physics information is in the red box. It's in these coefficients that depend on the tetrahedron side lengths and the L's, or angular momenta, of the basis functions. And note we have a sum over Li. So to summarize, we decompose the 4-point as a radial coefficient, which has all the physics, times an angular basis function, which is determined. And these angular basis functions are actually shown below in the second equation on the slide. They're basically combinations of 3 spherical harmonics proportional to a 3J symbol with angular momentum in the top row and Z component in the bottom row. And it turns out the Wigner-Eckart theorem says that any rotationally invariant tensor must be proportional to a 3J symbol. So we could have guessed that this was the correct combination for us to use. And the properties of these basis functions are summarized in a rather long paper that Robert Kahn, shown here on the slide, and myself have in Journal of Physics A in 2023. And it's a substantial tome, but it gives you all the properties of these functions that you will need to understand the basis. I should also say I've shown on this slide a diagram of a tetrahedron, and the way to visualize this all is to sit at the red point, which represents one galaxy, and look along the 3 side lengths, and the direction vectors of those sides are what's going into the angular basis function, and the lengths of those sides is what's going into the radial coefficient, zeta, L1, L2, L3. We also order the sides so that R1 is less than R2, less than R3, and this turns out to be essential for parity odd functions. So the basis that we have splits into even and odd modes. Even modes have an even sum of L1, L2, L3. Odd modes have an odd sum. and they have different behaviors under reflection. In particular, the odd modes capture any imbalance between tetrahedra and their mirror images. So the odd modes are only sensitive to a difference. They don't tell you how many of one type or another of tetrahedron you have. They just tell you if you have an imbalance between that type of tetrahedron and its mirror image. One way to visualize this is to sit on the left-hand image here and notice that if R1 is less than R2, less than R3, as I go around from shortest to longest side, I'm going around clockwise. In contrast, the right-hand tetrahedron here is the mirror image, and it's equivalent to taking R1 and pulling it through the plane formed by R3 and R2. So now, as I go from shortest to longest side, I'm going around counterclockwise. So you can think of the handedness of a tetrahedron as how you go around from shortest to longest from a given vertex. Mirror imaging, or inside outing the tetrahedron, actually will change that clockwise to counterclockwise. So geometrically, the odd modes are all proportional to the signed volume of the tetrahedron. You can calculate what's called the scalar triple product, and that's the lowest lying odd mode, which we call P111, and that is basically proportional to the signed volume of the tetrahedron. This makes sense because we started with the left-hand tetrahedron here, and as we pull R1 through the plane formed by R2 and R3, we're inside out in the tetrahedron, which corresponds to flipping the sign of the signed volume. So a parity transformation actually flips the sign of the signed volume of a tet, and therefore it makes sense that the odd modes are proportional to that. So just a quick slide to tell you, how do we actually measure the odd 4-point function on data? Well, we accelerate the measurement with GPUs. So this is a code called cadenza. At left, you see the cadenza to a Mozart piano concerto in the hand of Beethoven. And like a cadenza, which involves very fast playing and lots of notes, our code involves very fast processing of lots of galaxies. Galaxies are our notes. And in particular, the process of calculating the 4-point function in the isotropic basis is what we call high arithmetic intensity, lots of flops or floating point operations per second. And this turns out to work very well on GPUs. So we have this code called cadenza, which is a development of the Encore code for CPU. And this code computes the 2 through 6-point function, and for the 4-point function, which is of interest for this parity talk, we get 140x factor speed up over the CPU. This means that we can compute the 4-point function for all 1 million galaxies plus 32 times that number of randoms in BOSS in 30 minutes on one core. I should note that DESI Y1 has a similar number of galaxies, so the timing is similar. And this code was developed by myself, Craig Warner at UF, John Minhu, who's pictured here and was a postdoc in my group, as well as Bob and Daniel Eisenstein and Oliver Philcox on the CPU version. So now with these ingredients in hand, we can move to the data. How does the measured 4-point function look in our isotropic basis? So I'm showing you the radial coefficients. And what we've done here is we've mapped the dependence on the 3 side lengths. We've mapped that to a 1D index, and that's shown on the x-axis here. And then on the y-axis, we show the amplitude. And these different postage stamps are for different basis functions. So the top left one is 111, which is the lowest lying odd basis function. And then you've got 122, 144, and 212. Note that all of these L's sum up to an odd number. So these are the odd basis functions. We have 23 angular channels corresponding to different combinations of L's that we study. In what I'm showing you, we use 10 radial bins in each side, and as I've said, we've mapped the 3 radial bins to a 1D index. This is shown for legibility. Our fiducial analysis actually uses a much finer binning, but it's harder to read the plots. Now finally, in red, we're seeing results from the North Galactic Cap, and in blue, we're seeing results from the CMAS South Galactic Cap. You can't see through the center of our galaxy, so we split it into 2. And what I want you to really notice is that these measurements don't look like they have any obvious secure deviation from 0 by eye. They look kind of like noise. So what you really need to do is combine all 23 angular channels and then weight them by inverse covariance to get a detection significance. Okay, so I'm also showing you at right, just as a reminder, how our tetrahedron looks and what the 3 side lengths are in it. So these are our results. We combine those 23 postage stamps of which these four are examples, and we weight them by inverse covariance, and we do this for mocks with no parity violation, and we do this for data. So we did this for 2,000 mocks made for BOSS, called the patchy mocks, and they basically are just standard lambda CDM mocks done with a combination of perturbation theory and prescriptions to match n-body simulations. And you see that they form this histogram in terms of the total parity violating signal, which is basically the chi-squared away from 0. And this histogram has a width. We take that width to be our sigma, and we ask how far away is the data from the center of this histogram in units of the sigma. So our data in orange is 7 sigma discrepant from the Mach's null case distribution. So this work was reported in Hu, Slepian, and Khan 2023. Now, what I want to tell you about in the remainder of this talk is what we've done with DESI data. So DESI is the successor to BOSS. It stands for Dark Energy Spectroscopic Instrument, and it's at Kitt Peak National Observatory in Tucson, just outside of Tucson, Arizona. And you can see here that it is kind of at a commanding site. It's up above the ground to improve the wind baffling, and it has a really nice site sort of at the top of this mountain in the Tohono O'odham Nation. So DESI is, in contrast to BOSS, it's robotic, so it's much more efficient, and in fact, it's 90 times more efficient at getting spectra than BOSS and can get spectra of up to 150,000 objects per night. So here are our results from DESI. This plot is basically the same as the BOSS plot I showed you, but a little bit more is going on here. So here, the blue line is the data. Chi-squared is basically how distant from 0 is your signal in the parity odd sector. And the 3 colored histograms are 3 different types of mocks that we've used. The LRG in the title stands for luminous red galaxies, and we've indicated the redshift range, and also we're working on this plot in the North Galactic Cap. So the blue histogram, in cyan really, is the easy mocks. And these are mocks produced with Zeldovich approximation and an approximate fiber assignment scheme called fast fiber assign, or FFA. Then in red, we have actually n-body mocks. These are Abacus, which is a GPU-based n-body algorithm. And these are also fiber assigned with a very faithful scheme called alternative merged target ledger, or alt-MTL. And I should say fiber assignment is just how does each galaxy get assigned an optical fiber to be able to have its spectrum taken. So DESI has a relatively complicated pattern of fiber assign due to the robotic nature of the survey, and we need to model that in the mocks. And then finally, just for kicks, we show in yellow the Abacus FFA. This is the same n-body Abacus mocks as the red, but with a different fiber assignment scheme that's more approximate. So we believe the most faithful in terms of the dynamics and in terms of the fiber assign is the red. As I said, Abacus is n-body, easy mocks is not, and alt-MTL is the best approximate way of fiber assign we have. It's better than fast fiber assign, or FFA. That's why we've highlighted the red distribution here with a dark black curve. Now, what you can see immediately is that the blue DESI data line is quite far away from the center of the red distribution. What we can again do is ask what is the width of the red distribution, and then we can ask how far is the data from the center of the red distribution in terms of the width. And that's reported in the legend at top right. So it turns out we have 11.4 sigma evidence, DESI S sigma, for parity violation in the North Galactic Cap. And you can see basically that the DESI delta chi-squared from the center of the red distribution is 1,312, and the Abacus alt-MTL distribution in red is centered at 5,063 with a width of 115. So 1312 over 115 is about 11.4, and that's how we're getting this DESI significance. So we can also look at the same thing in the South Galactic Cap, and there, with the same meaning for all the mocks distribution, and again comparing to the red Abacus alt-MTL, we find 7 sigma evidence for parity violation in the South. Now, it's expected that the South would have lower evidence than the North because the volume of the South is somewhat smaller, and also the number density of objects in the South is somewhat lower because of the survey strategy of DESI. Okay, So I've shown you that in both the North and the South, we're seeing evidence for parity violation in DESI. Now I want to talk about a different analysis that we can do. We can basically split the DESI North and South into patches, which are shown here for the North. So blue is one patch, kind of rose is patch 2. Pink is patch 3, and dark crimson is patch 4. And we don't use the two red areas at the bottom around RA of 150 and RA of 200. We don't use those for this patch analysis. And so what we do is we measure the 4-point function signal on each of these patches. Now, if the parity violating signal is really due to inflationary physics, it should be the same everywhere. So if you cross-correlate these patches, then you should see a non-vanishing cross-correlation. However, if the parity violating signal we see is actually due to underestimate of the noise, then we would expect that to be random, so you shouldn't see any cross-correlation. So this cross-correlation method is very powerful to protect us from underestimate of the noise that we may have underestimated the noise. So here we used the EasyMock FFA, so approximate dynamics and approximate fiber assign, and we applied the cross-correlation method to them in the North Galactic Cap with the geometry I showed on this previous slide. And we also applied this cross-correlation method to the data. So here we actually remarkably find consistency between the data and the mocks. In other words, we don't see any particular evidence for parity violation in the data beyond what the mocks are telling us, and we know the mocks were created with no parity violation. Now you might wonder, why can't we use the Abacus AltMTL mocks for this cross-correlation? Well, those were produced using replication. They basically took a small box and made a bunch of copies of it and then cut the survey out of that. And so because of that replication, you would naturally have cross-correlation in different regions of the sky because you've actually duplicated the same underlying box. So the Abacus would not be a good null case for cross-correlation because it would actually have a cross-correlation spuriously. Okay, we also do the same thing with the South. These are our 3 patches in the South in green, red, and blue where we do this cross-correlation method. And again, in the South, we find that in the cross, the data is consistent with the mocks. In other words, no evidence for parity violation. So we're left with a pretty interesting story, which is that we see extremely strong evidence, 11 sigma and 7 sigma in the North and South for parity violation, using one test for parity we can perform, but then using another test, which is more robust but may not be as sensitive, we don't see evidence. So how do we fix this? Well, we just wait for DESI year 3 and year 5. This is a forecast for DESI year 5, i.e. the final data, assuming that our 5 sigma or so evidence in the BOSS survey is real. So how to read this plot is go to the black vertical line. That's showing you the number density that our BOSS sample actually was at, and we fixed that to be about 5 sigma. In reality, in BOSS it was 7, but to make a round number, we fixed it to 5. Then what we did is we simulated using covariances with different number densities. That generated this black curve of other possible BOSS results to show you how the result depends on number density. And then we evaluated at the fiducial DESI number density shown by the red vertical dashed line, what year 5 of DESI would actually get us if the BOSS result is real. Now you can see that the DESI year 5 gets us about 40 sigma if the BOSS result is real at 5 sigma, and that's in the LRG sample. You can also see that in the emission line galaxy sample in blue, DESI year 5 will get us a healthy detection if the BOSS signal is indeed real. So this forecast was shown in a paper by Bob, Khan, myself, and Jamin, who in 2022 in PRL. And basically the point is, DESI's data is going to be so ample and so good that to solve this tension, we just have to wait and see what DESI year 5 says. So I don't have time to talk about it today, but in terms of other work that my group is doing on parity, please feel free to ask me about using the CMB lensing trispectrum to probe parity. the sensitivity of the CMB primary trispectrum at low L, which we can prove is not very sensitive to parity. And also please ask me or William Ortola Leonard, my student, about one-loop contributions to the 4-point function covariance, which can improve the robustness of our parity violation search. So to summarize, I've shown you that the Galaxy 4-point function is sensitive to parity violation. I've mentioned a fast algorithm to compute it and how we exploit the GPU. I've shown you that we measured this on 1 million galaxies in BOSS and 1 million galaxies of DESI Y1 data, and we see statistically significant evidence in the auto chi-squared, but not in the cross correlation of patches. So I think the summary here is we live in exciting times. We don't really know whether the parity violation is genuinely of inflationary origin or not, but with DESI year 3 and year 5 coming up, we're pretty much poised to find out.